Something surrounds you, bombards you, some of which you can't see, touch, or even feel. Every day, everywhere you go. It is odorless and tasteless, yet you use it and depend on it every hour of every day. Without it, the world you know could not exist. What is it? Electromagnetic radiation. These waves spread across a spectrum from very short gamma rays to X-rays, ultraviolet rays, visible light waves, even longer infrared waves, microwaves, to radio waves which can measure longer than a mountain range. This spectrum is the foundation of the information age and of our modern world. Your radio, remote control, text message, television, microwave oven, even a doctor's X-ray, all depend on waves within the electromagnetic spectrum. Electromagnetic waves, or EM waves, are similar to ocean waves in that both are energy waves. They transmit energy. EM waves are produced by the vibration of charged particles and have electrical and magnetic properties. But unlike ocean waves that require water, EM waves travel through the vacuum of space at the constant speed of light. EM waves have crests and troughs like ocean waves. The distance between crests is the wavelength. While some EM wavelengths are very long and are measured in meters, many are tiny and are measured in billionths of a meter, nanometers. The number of these crests that pass a given point within 1 second is described as the frequency of the wave. One wave, or cycle, per second is called a hertz. Long EM waves, such as radio waves, have the lowest frequency and carry less energy. Adding energy increases the frequency of the wave and makes the wavelength shorter. Gamma rays are the shortest, highest energy waves in the spectrum. So, as you sit watching TV, not only are there visible light waves from the TV striking your eyes, but also radio waves transmitting from a nearby station, and microwaves carrying cell phone calls and text messages, and waves from your neighbor's Wi-Fi, and GPS units in the cars driving by. There is a chaos of waves from all across the spectrum passing through your room right now. With all these waves around you, how can you possibly watch your TV show? Similar to tuning a radio to a specific radio station, our eyes are tuned to a specific region of the EM spectrum and can detect energy with wavelengths from 400 to 700 nanometers, the visible light region of the spectrum. Objects appear to have color because EM waves interact with their molecules. Some wavelengths in the visible spectrum are reflected and other wavelengths are absorbed. This leaf looks green because EM waves interact with the chlorophyll molecules. Waves between 492 and 577 nanometers in length are reflected, and our eye interprets this as the leaf being green. Our eyes see the leaf as green, but cannot tell us anything about how the leaf reflects ultraviolet, microwave, or infrared waves. To learn more about the world around us, scientists and engineers have devised ways to enable us to see beyond that sliver of the EM spectrum called visible light. Data from multiple wavelengths help scientists study all kinds of amazing phenomena on Earth, from seasonal change to specific habitats. Everything around us emits, reflects, and absorbs EM radiation differently based on its composition. A graph showing these interactions across a region of the EM spectrum is called a spectral signature. Characteristic patterns, like fingerprints within the spectra, allow astronomers to identify an object's chemical composition and to determine such physical properties as temperature and density. NASA's Spitzer Space Telescope observed the presence of water and organic molecules in a galaxy 3.2 billion light-years away. Viewing our Sun in multiple wavelengths with the SOHO satellite allows scientists to study and understand sunspots that are associated with solar flares and eruptions harmful to satellites, astronauts, and communications here on Earth. We are constantly learning more about our world and universe by taking advantage of the unique information contained in the different waves across the EM spectrum. All electromagnetic radiation is light. Visible light is the only part of the spectrum you can see. For all your life, your eyes have relied on this one narrow band of EM radiation to gather information about your world. Though our sun's visible light appears white, it is really the combined light of the individual rainbow colors with wavelengths ranging from violet at 380 nanometers to red at 700 nanometers. Before Isaac Newton's famed experiment in 1665, people thought that a prism somehow colored the sun's white light as it bent and spread a sunbeam. Newton disproved this idea by using two prisms. To show that white light is made up of the bands of colored light, Newton used a second prism to show that the bands of colored light combine to make white light again. Visible light contains important scientific clues that reveal hidden properties of objects throughout the universe. Minute gaps in energy at specific visible wavelengths can identify the physical condition and composition of stellar and interstellar matter. Human eyes aren't nearly sensitive enough to detect these faint peaks, but scientific instruments can. Scientists can learn the composition of an atmosphere by considering how atmospheric particles scatter visible light. Earth's atmosphere, for example, generally looks blue because it contains particles of nitrogen and oxygen, which are just the right size to scatter energy with the wavelength of blue light. When the sun is low in the sky, however, light travels through more of the atmosphere and more blue light is scattered out of the beam of sunlight before it reaches your eyes. Only the longer red and yellow wavelengths are able to pass through, often creating breathtaking sunsets. When scientists look at the sky, they don't just see blue, they see clues about the chemical composition of our atmosphere. However, visible light reveals more than just composition. As objects grow hotter, they radiate energy with a shorter wavelength, changing color before our eyes. Watch a flame shift from yellow to blue as it is adjusted to burn hotter. In the same way, the color of stellar objects tells scientists much about their temperature. Our sun produces more yellow light than any other color because of its surface temperature. If the sun's surface were cooler, say 3000 degrees Celsius, it would look reddish, like the stars Antares and Betelgeuse. If the sun were hotter, say 12,000 degrees Celsius, it would look blue, like the star Rigel. Like all parts of the electromagnetic spectrum, visible light data can also help scientists study changes on Earth, such as assessing damage from a volcanic eruption. This NASA EO1 image combines both visible and infrared data to distinguish between snow and volcanic ash and to see vegetation more clearly. Since 1972, images from NASA's Landsat satellite have combined visible and infrared data to allow scientists to study changes in cities, neighborhoods, forests, and farms over time. Visible light images taken by NASA's Mars landers have shown us what it would look like to stand on another planet. They have expanded our minds, our imagination, and our understanding. NASA instruments can do more than passively sense radiation. They can also actively send out electromagnetic waves to map topography. The Mars Orbiting Laser Altimeter sends a laser pulse to the surface of the planet, and sensors measure the amount of time it takes for this laser signal to return. The elapsed time allows the calculation of the distance from the satellite to the surface. As the spacecraft flies above hills, valleys, craters, and other surface features, the return time varies and provides a topographic map of the planet's surface. Back in Earth orbit, NASA's IceSat mission uses the same technique to collect data about the elevation of the polar ice sheets to help monitor changes in the amount of water stored as ice on our planet. Laser altimeters can also make unique measurements of the heights of clouds, the top of the vegetation canopy of forests, and can see the distribution of aerosols from sources such as dust storms and forest fires. Finally, visible light helps us to explore the far reaches of the universe that humans could not hope to reach physically. Using visible light, the Hubble Space Telescope has created countless images that spark our imagination, inflame our curiosity, and increase our understanding of the universe. Guglielmo Marconi's first radio transmissions in 1894 have spread into space for over 100 years at the speed of light. They passed Sirius in 1903, Vega in 1919, and Regulus in 1971. That signal has already passed over 1,000 stars. Anyone orbiting one of those stars with a really good receiver could detect Marconi's signal and know that we are here. Radio waves are the longest and contain the least energy of any electromagnetic wave. While visible light is measured in minute fractions of an inch, radio waves vary from about 19 centimeters, about the length of a water bottle, to waves the length of cars, ships, mountains, all the way up to monstrous waves longer than the diameter of our planet. Heinrich Hertz discovered radio waves in 1888. The first commercial radio station went on the air in Pittsburgh, Pennsylvania on November 2, 1920. Then, in 1932, a major discovery by Carl Jansky at Bell Labs revealed the stars and other objects in space radiated radio waves. Radio astronomy was born. However, scientists need giant antennas to detect weak, long-wavelength radio waves from space. The enormous Arecibo radio dish antenna measures 305 meters in diameter, over 3 football fields. Scientists can link the signals from an array of separate radio antennas to focus on tiny slices of distant space. Such arrays act as a single immense collector. This giant New Mexico array uses 27 parabolic dish antennas shaped into a giant Y, with each arm capable of stretching for 13 miles. Scientists have even spread these linked antennas across the globe. One of the largest stretches from Hawaii to the Virgin Islands and acts like such a powerful telephoto lens that a baseball sitting on the moon would fill its entire field of view. Many of the greatest astronomical discoveries have been made using radio waves. Pulsars, the existence of giant clouds of superheated plasma, which are among the largest objects in the universe, and even quasars, such as this one over 10 billion light-years away, were all discovered using radio waves. Radio waves also provide more local information. Astronomical objects that have a magnetic field usually produce radio waves, such as our Sun. Thus, NASA's STEREO satellite is able to monitor bursts of radio waves from the Sun's corona. Wave sensors on the WIND spacecraft record the radio waves emitted by a planet's ionosphere, such as the bursts from Jupiter, whose wavelength measures about 15 meters. Radio waves fill the space around us to bring entertainment, communications, and key scientific information. We can't hear these radio waves. When you tune your radio to your favorite station, the radio receives these electromagnetic radio waves and then vibrates a speaker to create the sound waves we hear. We may not be able to tap our toes to the cosmic radio transmissions, but we certainly discovered much about our universe's grand cosmic dance by listening to them. When you use a remote control to change channels on your TV, your remote is using light waves. But this light is beyond the visible spectrum of light you can see. Back in 1800, William Herschel conducted an experiment measuring the temperature changes between the colors of the spectrum, plus one measurement beyond visible red. When that thermometer registered a temperature warmer than all the other colors, Herschel had discovered another region of the electromagnetic spectrum: infrared light. This region consists of short wavelengths around 760 nanometers to longer wavelengths about 1 million nanometers, or about 1,000 micrometers in length. We can sense some of this infrared energy as heat. Some objects are so hot they also emit visible light, such as a fire. Other objects, such as humans, are not as hot and only emit infrared waves. We cannot see these infrared waves with our eyes alone. However, instruments that can sense infrared energy, such as night vision goggles or infrared cameras, allow us to see these infrared waves from warm objects like humans and animals. Infrared energy can also reveal objects in the universe that cannot be seen with optical telescopes. Infrared waves have longer wavelengths than visible light and can pass through dense regions of gas and dust with lower scattering and absorption. When you look up at the constellation Orion, you see only the visible light. But NASA's Spitzer telescope was able to detect nearly 2,300 planet-forming disks in the Orion Nebula by sensing the infrared glow of their warm dust. Each disk has the potential to form planets and its own solar system. Incoming ultraviolet, visible, and a limited portion of infrared energy, together sometimes called shortwave radiation, from the Sun drives our Earth system. Some of this radiation is reflected off of clouds, and some is absorbed in the atmosphere. Larger aerosol particles in the atmosphere interact with and absorb some of the radiation, causing the atmosphere to warm. The heat generated by this absorption is emitted as long-wave infrared radiation, some of which radiates out to space. The solar radiation that does pass through Earth's atmosphere is either reflected off snow, ice, or other surfaces, or is absorbed by the Earth's surface. This absorption of radiation warms the Earth's surface, and this heat is emitted as long-wave radiation into the atmosphere, which allows only a small amount to radiate out to space. Greenhouse gases in the atmosphere, such as water vapor and carbon dioxide, absorb most of this emitted long-wave infrared radiation, and this absorption heats the lower atmosphere. In turn, the warmed atmosphere emits long-wave radiation, some of which radiates towards the Earth's surface, keeping our planet warm and generally comfortable. The energy entering, energy reflected, energy absorbed, and energy emitted by the Earth system constitutes the components of the Earth radiation budget. A budget that's out of balance can cause the temperature of the atmosphere to increase and eventually affect our climate. For scientists to understand climate, they must also determine what drives the changes within the Earth's radiation budget. The CERES instrument aboard NASA's Aqua and Terra satellites can measure the reflected shortwave and emitted long-wave radiation into space accurately enough for scientists to determine the Earth's total radiation budget. Other NASA instruments monitor the changes in other aspects of the Earth's climate system, such as clouds, aerosol particles, or surface reflectivity, and scientists are examining their many interactions with the energy budget. A portion of solar radiation from the Sun that is just beyond the visible spectrum is referred to as near-infrared. Scientists can study how this radiation reflects off the Earth's surface to understand changes in land cover, such as growth of cities or changes in vegetation. Our eyes perceive a leaf as green because wavelengths in the green region of the visible light spectrum are reflected, while other visible wavelengths are absorbed. Yet the chlorophyll and the cell structure of the leaf are also reflecting near-infrared light, light we cannot see. This reflected near-infrared radiation can be sensed by satellites, allowing scientists to study vegetation from space. Using these data, scientists can identify some types of trees, can examine the health of forests, and can even monitor the health of vegetation, such as forests infested with pine beetles or crops affected by drought. Studying the emission and reflection of infrared waves helps us to understand the Earth system and its energy budget. Near-infrared data can also help scientists study land cover such as changes in snow, ice, forests, urbanization, and agriculture. Scientists are beginning to unlock the mysteries of cooler objects across the universe such as planets, cool stars, nebulae, and much more using infrared waves. Microwaves can pop your popcorn. They can catch you speeding. They carry thousands of phone channels to speed your calls. But can microwaves help us learn about our world and our universe? Let's find out. With wavelengths ranging from 30 centimeters down to 1 millimeter, microwaves fall between radio waves and infrared. Microwaves are used in Doppler radar, which is widely used for short-term localized weather forecasting and what you see on TV weather news. Satellites have revolutionized weather forecasting by providing a global view of weather patterns and surface temperatures. This unique perspective has greatly increased the accuracy of tropical storm and climate forecasts. Different wavelengths of microwaves, grouped into bands, provide different information to scientists. Medium-length, C-band microwaves penetrate through clouds, dust, smoke, snow, and rain to reveal the Earth's surface. Satellite microwave measurements reveal the full Arctic sea ice cover every day, even where clouds exist. These measurements show great variability from year to year, but also an overall decrease in Arctic sea ice since the late 1970s, illustrated here with maps and a time series of Arctic sea ice in September at the end of the summer melt. The Japanese Earth Resources satellite uses longer wavelength L-band microwaves for forest mapping by measuring surface soil moisture, such as this image of the Amazon basin, to identify areas of recent deforestation. L-band microwaves are also used by global positioning systems, such as the one in your car. Scientists routinely combine microwave information with information from other parts of the EM spectrum to study the composition of cosmic dust or of a supernova, such as this supernova image that combines X-ray, radio, and microwave data. This recently known supernova in the Milky Way exploded just over 140 years ago at the time of the American Civil War. One important phenomenon is unique to microwaves. In 1965, using long L-band microwaves, Arno Penzias and Robert Wilson made an incredible accidental discovery. They detected what they thought was noise from their instrument, but was actually a constant background signal coming from everywhere in space. This radiation is called cosmic microwave background, and if our eyes could see microwaves, the entire sky would glow with a nearly uniform brightness in every direction. The existence of this background radiation has served as important evidence supporting the Big Bang theory for how our universe began. Microwaves have become both staples and wonders of modern life. They are also the backbone of communications and of Earth's sensing systems, and they are an excellent guide to the ancient history and origins of our universe. Swirling spiral arms of galaxy M33 can be seen in visible light, but the true extent of these spiral arms are revealed in ultraviolet light. Just as a dog can hear a whistle just outside the range of human hearing, bugs can see light just outside the range our eyes can see. A bug zapper emits this ultraviolet light to attract insects. Johann Ritter conducted an experiment in 1801 to find out what, if any, electromagnetic waves are beyond violet. Ritter knew that photographic paper would turn black more rapidly in blue light than in red light, so he tried exposing the paper beyond the violet end of the visible spectrum. Sure enough, the paper turned black, proving the existence of light beyond violet, ultraviolet rays. These ultraviolet rays, or UV radiation, vary in wavelength from 400 nanometers to 10 nanometers and can be subdivided into three regions: UVA, UVB, and UVC. Visible light from the sun passes through the atmosphere and reaches the Earth's surface. UVA, long-wave ultraviolet, is the closest to visible light. Most UVA also reaches the surface, but shorter wavelengths, called UVB, are the harmful rays that cause sunburn. Fortunately, about 95% of these harmful UVB rays are absorbed by ozone in the Earth's atmosphere. UVC rays are the shortest and most harmful and are almost completely absorbed by our atmosphere. The ozone monitoring instrument aboard NASA's Aura satellite detects ultraviolet radiation to help scientists study and monitor the chemistry of our atmosphere, including UV-absorbing ozone. While atmospheric protection from harmful UV radiation is good for humans, it complicates the study of naturally produced UV rays in the universe by scientists here on the Earth's surface. Young hot stars shine most of their light beyond the visible light spectrum at ultraviolet wavelengths. Scientists need telescopes in orbit above the Earth's UV-absorbing atmosphere to find and study these UV-bright regions of star formations in distant galaxies. New young stars in the spiral arms of galaxy M81 can be seen in this Galaxy Evolution Explorer GALEX image from NASA. Chemical substances, both atoms and molecules, interact with UV light, making this region particularly interesting to scientists. An ultraviolet instrument aboard Cassini has detected hydrogen, oxygen, water ice, and methane in the Saturn system. UV data have also revealed details of Saturn's aurorae. Scientists also use UV waves shining from distant stars to view permanently shadowed regions of lunar craters. The Lyman Alpha Mapping Project, or LAMP, instrument aboard NASA's Lunar Reconnaissance Orbiter can use this faint starshine to look for possible water ice on the Moon. Ultraviolet rays may be harmful to humans, but they are essential to studying the health of our planet's protective atmosphere and give us valuable clues to the formation and composition of distant celestial objects. Created by the hottest, most violent, and most energetic objects and events in the universe, gamma rays travel across vast stretches of space, only to be absorbed by Earth's atmosphere. Scientists had no way to detect and study gamma rays from the cosmos until high-altitude balloons and rockets carried gamma ray sensors above the atmosphere. Deadly to humans, gamma rays are created on Earth by natural radioactive decay, by nuclear explosions, and even by the lightning and thunderstorms. Coronal mass ejections from our sun emit gamma rays, followed by masses of charged particles. Monitoring these gamma rays provides scientists with an early warning of incoming charged particles that may cause disruptions in power and communication networks. The most energetic of all EM waves, gamma rays carry enough energy to kill living cells. Doctors are able to selectively use gamma radiation to destroy cancer growths. Gamma ray wavelengths are the shortest of all electromagnetic waves, about the size of an atom's nucleus. In fact, it is so short that the rays sail through atoms as easily as comets sail through our solar system. This makes detecting gamma rays difficult for scientists. Gamma ray detectors typically contain densely packed crystal blocks. As gamma rays pass through, they collide with electrons in the crystal. The sensor doesn't directly detect gamma rays. Rather, it detects the charged particles created by those collisions. Scientists have used gamma rays to determine the elements that make up Martian surface soils. When struck by cosmic rays, chemical elements in soils and rocks emit uniquely identifiable signatures of energy in the form of gamma rays. The Gamma Ray Spectrometer on NASA's Mars Odyssey orbiter detects and maps these signatures, such as this map of hydrogen concentrations. Gamma rays stream from stars, supernovas, black holes, and pulsars to wash our sky with gamma ray light. NASA's Fermi Gamma Ray Space Telescope imaged the location of these sources, mapping out the Milky Way galaxy by creating a full 360-degree view of the galaxy from our perspective here on Earth. While the visible light sky is predictable and follows regular patterns, the gamma ray sky does not. Bursts of high-energy gamma radiation arrive from deep space every day. These explosions of gamma rays last fractions of a second to minutes, popping like cosmic flashbulbs, momentarily dominating the gamma ray sky and then fading. This video of the Vela pulsar beams gamma rays every 89 seconds as it rotates. Gamma ray bursts are the most energetic and luminous electromagnetic events since the Big Bang, and can release more energy in 10 seconds than our sun will emit in its entire 10 billion year expected lifetime. NASA's SWIFT satellite recorded this gamma ray burst of an exploding star 13 billion light years away. It is among the most distant objects ever detected when the universe was just 630 million years old. A recent observation of a gamma ray burst produced the greatest total energy to date, equivalent to 9,000 typical supernovae. By continuing to study gamma rays, we will unlock important new understanding in astronomy, its use in medical treatments, and allow us to further enhance our protection for our satellites and other electronics here on Earth. A star explodes in a blinding supernova, spraying X-rays across the galaxy to tell its tale. X-rays also tell a dentist which tooth to drill and a surgeon which bones to mend. In 1895, Wilhelm Röntgen discovered that firing streams of X-rays through arms and hands created eerie, but detailed, images of the bones inside. X-rays are high-energy light rays with wavelengths between 3 and 0.03 nanometers. so small that some X-rays are no bigger than many individual atoms. In laboratories, scientists fire beams of X-rays at unknown substances to learn what elements they contain and to decode their atomic structure. This is how scientists unraveled complex molecules like penicillin and DNA. Scientists can also detect the X-rays emitted from extremely hot and energetic objects in the universe. NASA's robotic rovers recorded X-rays to identify the spectral signatures of elements, such as zinc and nickel, in Martian rocks. X-rays can also reveal an object's temperature, since temperature determines the wavelength of its radiation. The hotter the object, the shorter that wavelength is. X-rays come from objects that seethe at millions of degrees, such as pulsars, black holes, supernovas, or the plasma in our sun's corona. Our sun has a surface temperature of around 6,000 degrees Celsius and radiates most of its energy in visible wavelengths. But it is easier to study the massive energy flows in the corona's energetic plasma by observing X-rays, like this image from the Hinode satellite, a joint Japanese-NASA mission. NASA's SOHO satellite produced these X-ray images of the sun that allow scientists to see and record these energy flows within the corona. NASA's orbiting Chandra X-ray Observatory detects X-rays created by objects spread far across space, such as this supernova explosion that occurred 10,000 light-years from Earth. The colors in the gas and dust cloud correspond to different energy levels of the X-rays created by the blast. X-rays at different wavelengths provide information about an object's composition, temperature, density, or its magnetic field. Human eyes may not be able to see X-rays, but from seething cosmic bodies to individual atomic elements, X-rays provide a wealth of information to exploring scientists.